3.4 example 1 gets us to start to analyze some graphs of polynomial functions. And we're going to take A and B kind of separately. And some pretty common questions when you talk about polynomials are, the least possible degree, whether the leading coefficient is positive or negative, x-intercepts with their degrees. And this least possible degree piece is ultimately multiplicity. Multiplicity tells us the least possible degree on there. And then finally, the intervals where the function is positive and the intervals where it's negative. I just like to talk about that the function is positive if it's above the x-axis, and the function is negative if it's below the x-axis. And we're talking about the output, so that's the y value sign that we're caring about. All right, so the first graph, it gives us the graph for A right here, clearly from a calculator screen, which is nice because it gives us some values. We're going to find the least possible degree. Now, the least possible degree I'm going to put right here is the sum of the multiplicities. And the reason why it says least possible degree is every now and again, one of your factors might not have a value of x that makes it 0. If one of my factors was x squared plus 1, x squared plus 1 is never 0. But it would certainly, modify the possible degree of that function. So the least possible degree for this function, I'm just going to summarize that we have x-intercepts at x equals -4, x equals -2, and x equals 2. And all three of these, judging by the shape of that graph, have multiplicity of 1. And that means if we add 1 to itself, 3 times, my least possible degree, I'll just put least possible degree, is going to be the sum of those multiplicities, and therefore that's going to be 3. Now, once you know the least possible degree, that ultimately tells you what end behavior we should expect. And I want to draw both, that if we knew we were looking at a degree 3, we're going to look if it had a positive leading coefficient, it should look something like that. If it had a negative leading coefficient, it should look something like this. And that's from 3.1 in this chapter. So I think we all agree, judging by the graph, that we would have a positive leading coefficient because it does look like our standard y equals x cubed. All right, so the x-intercepts and the factors of the function with least possible degrees. I've already identified the x-intercepts, and I want to write it out that what that means is that this function, again, a vertical stretch is possible. We could write this as x minus -4 because -4 would make that 0, x minus -2 because -2 would make that 0, and then finally x minus 2. Now, it's really important that that's very similar to what we did with long division, but the one thing I would recommend you do is instead of writing, x minus -4, simplify that. So that's going to be x plus 4, -4 still makes that 0, x plus 2, -2 still makes that 0, and then finally x minus 2 we won't touch. All right, now looking on my graph for the intervals where the function is positive and negative, I really cannot emphasize enough that 0 is neither positive nor negative. So you are not going to be using square brackets when you talk about intervals. Now, what I'm going to do to try to hammer home that interval notation one more time, because we've talked about it in Math 20, but we have to get used to it. We're going to look at where it's positive, and we're going to look at where it's negative. Well, the function is negative when x is less than -4. So that's from this point, and I'll draw that open dot, sorry. So that's from this point to -infinity. And then it's also negative right here. And I'll try to just kind of mark that up a little bit on the graph. So it's when x is less than 4, and it's when x is greater than -2, but less than +2. We'll write interval notation for these in a second. The function is positive during the red sections, so that's in between these two, and it's from +2 to infinity. So I'm going to write that as x is greater than +2, and then my other interval is going to be that x is greater than -4, but less than -2. All right, now really importantly, the function is positive, negative, or 0. So not considering the x-intercepts, we know it's 0 there, those 4 inequalities should cover the entire number line from -infinity to +infinity. And that's part of why I like doing interval notation. It's a little bit easier to see. So writing these out in interval notation, if x is less than -4, that means that -infinity is the lower bound and -4 is the upper bound. If x is greater than -2 and less than +2, -2 is the lower bound and +2 is the upper bound. For the red, or when the function is positive, if x is greater than 2, 2 is the lower bound, and infinity is the upper bound. And between -4 and -2, -4 is the lower bound, and -2 is the upper bound. Now, what I'd like to do is at least once show on a number line how we have now described every interval possible. And this is going to build some skills that we use in calculus. And I just want to put the x-intercepts on there. So -4, -2, and then +2. The spacing doesn't particularly matter because this is just a visual. I'm going to put where the function is positive kind of above. So from -4 to -2 is that interval. From 2 to infinity is this interval. And then where the function is negative, I'm just going to switch these to blue to get a nice little color coordination. We would have the interval -infinity to -4 and the interval -2 to +2. Now, I hope we agree that looking at the intervals kind of listed like that, we can see that that covers the entire X number line. All right, really importantly, the reason we don't use square brackets, that, and I want to write this out because I've used function notation, that the function at -4 is 0, which is neither positive nor negative. The function at -2 is 0, and the function at 2 is 0. Really important to remember that x-intercepts describe when the value of the function, or the output, or the y would be 0. Okay, the second graph here, we're doing the same thing. We're judging a few different things along the way. The least possible degree, I'm going to do the same thing I did in the previous question. So I'm going to identify the x-intercepts. So my x-intercepts, I have one at x equals -5. I have one at x equals -1. And then I have one at x equals 4. I don't know why that slash is there. It doesn't need to be there. Now, what I'm going to do, though, is because we need to worry about multiplicity, I'm just going to put the multiplicity down here. X equals 5 is multiplicity 1. The graph is just moving through that x-intercept. X equals -1 has multiplicity 1 as well, but x equals 4 has multiplicity 2. And that's a really important consideration, that because the graph is changing direction and touching that x-axis, that tells us that it has multiplicity 2. So looking at those three factors, I think it's a good idea to write it in factored form right away. So I'm going to say that this function, let's use f of x again, it could have a vertical stretch, but then we know that our x-intercepts would be x minus -5, and I'll put to the power of 1 there. Then we'd have x minus -1, again to the power of 1, but then I would have x minus 4 to the power of 2 because of its multiplicity. Now, again, a little simplification is a good idea. So we have a times x plus 5 times x plus 1 times x minus 4 squared. And now we can look at the sum of that multiplicity. So our least possible degree is going to be the sum of those exponents. So 1 plus 1 plus 1, and we get that the least possible degree is 4. Now we need to think about the leading coefficient. If I look at a quartic, and I'm going to draw them again, we could talk about the general form of that quartic with a positive and a negative leading coefficient. I would just draw y equals x to the power of 4, which looks like this, as one x-intercept with multiplicity 4. This is when the leading coefficient is positive. This is when the leading coefficient is negative. Now, please remember that the leading coefficient tells us about the end behavior of the graph. And if we look at our given function, let me draw the arrows on there, we can see that it matches the end behavior of a negative leading coefficient. So we know that the leading coefficient is negative. Now, all that really tells me is the a value would be less than 0 in my description right here, in my f of x function. All right, what we need to do now is we've actually done some of this, right? We've written the x-intercepts and the factors of the function with the least possible degree. We know that's good. Finally, we need to list the intervals where the function is positive and the intervals where it's negative. I don't know if I can move this graph. Oh, it's locked. I'm just going to move it so we can see that. I'd like to show that kind of concept that you don't have to write the number line every time, but it is beneficial to think about what those intervals are marked. So I am going to write when f of x is less than 0, so it's negative, in black. And I'm going to write when f of x is greater than 0 in red. And I'll mark this up on the diagram as we go. So f of x is less than 0, greater than 0 we'll do first, between -5 and -1. And I'm going to use interval notation here. So -5 is my lower bound, and -1 is my upper bound. And x exists between those two numbers. All right, the function is negative from -infinity to -5. So -infinity to -5. And from -1 to +4. And then finally, we are going to have from +4 to infinity. Now, a lot of students get frustrated. Why can't I just go -1 to positive infinity? And I would encourage you to think about, what is the function evaluated at 4? Is it greater than or less than 0? It's neither. F of 4 is equal to 0. And it's why we can't include that in this interval. It almost looks like there's a missing x value, and there is, because when x is 4, the function is neither positive nor negative, so we can't include it in those intervals. Again, worth mentioning that, I drew it on the graph. If you look at the black plus the red plus the black plus the black, that involves every single number on the number line except for the x-intercepts. Right, so that's a bit of a taste of what it looks like to use multiplicity to evaluate or analyze polynomial functions.